Welcome back, students, for the lecture series on analysis of indeterminate structures, 18 CV 52. We are in module 4. That is, we are going to start today with the module 5, final modules, lecture number 42. So, in the previous classes, we have studied about analysis of continuous beams, frames, truss, band frames. All were being analyzed by using flexibility matrix method. And today we are going to start with a new chapter, that is stiffness matrix method. It is also same like flexibility. Instead of flexibility, we are dealing with stiffness here. Stiffness means we are going to find the stiffness of individual members at the joints where we require. And we are forming a same comparative to equations what we have done in the flexibility, and we are finding the unknown. So in this stiffness matrix can be also called as a displacement method. Why it is called displacements means the displacements are taken as basic unknowns in this method. Means the rotations at individual joints are taken as unknowns, and we find the displacement at that point. So it is called as displacement method. And we are using equilibrium methods here. Means equilibrium equations are being applied here and formed and solved the problems. That's what it's also called as equilibrium method. Since the method of solving is by stiffness finding in each member, it is also called as stiffness matrix method. So this can be called by any of the three methods here. Usually in flexibility, what we did, we found the static indeterminacy, where unknowns were the displacement delta, and we found that. But here in stiffness matrix, we are going to find the kinematic indeterminacy. So kinematic indeterminacy means it is a degree of freedom. As you all know, what is degree of freedom? At a joint, when a support conditions is given, we will check whether in which direction it is free to work. So degree of freedom, that is what we are finding at the individual joints here. So usually in general, instead of finding all that, we are going to find the slope at every joints, that is rotations. We'll come to know later on when we take one problem and solve it. So it will be easy for you to understand exactly what are the method followed in stiffness. So let us first do the step-by-step procedure for solving of stiffness matrix method. These are the following steps which are used to analyze. Usually there are 8 steps. So whenever a problem is given, whether it is continuous beam, whether it is band frame, whether it is frame, whether it is truss, whichever will be the condition, whenever a structure is given, our first step is to determine the degree of kinematic indeterminacy. That is number of degree of freedom at each joint will be known. That will become the number of unknowns here. So number of unknowns will be in the form of degree of kinematic indeterminacy or the degree of freedom, what we call. The second step is once we know the degree of kinematic indeterminacy, we are going to select sum of the joints, means sum of the forces, which mean assumed as indeterminacy. So we are going to assign coordinate at that displacement point in the direction what we have removed. Third step, we assume all ends are fixed end. That individual member we will separate and we assume them as a fixed end, and we are going to find the fixed end moments. That is third step. Fourth step, as we know individual coordinate directions is known, we are going to find the coordinate value at determine the PL. That I will tell whenever you solve the problem, you come to the value of PL. PL will be found at each coordinate directions. Fifth step, determine the stiffness matrix, that is K value, by giving a unit load or unit displacement at a displacement point in the same directions. Then sixth one will observe the final forces in various coordinate directions. Find the final forces, that is P value. Once you know the P value, PL value, and stiffness K, form and solve the stiffness equation. That is K is equal to delta is equal to P minus PL. K is known, P is known, PL is known, only delta is unknown here, displacements. Calculate the members by using joint displacement methods. So these are the following steps we need to follow while finding the unknowns in the stiffness matrix method. So for this, let us take one of the example so that it will be easy for you to convenient for you to see how it can be solved. The same problem was been solved in the executive matrix method first problem. The same problem is taken to check whether we get the same movements what we have got in flexibility or not. So here is the first problem. Analyze the continuous beam shown in the figure by displacement method. Take EI constant throughout. ABC is a continuous beam with A and is fixed, B and C and is having a roller supports. First span AB is subjected to a UDL of 60 kilonewton meter, the span of 4 meter to the entire span. Then BC member is subjected to a point load of 100 kilonewton, which is acting at a midspan of the member, having a 3 meters total span. Means the 100 meters acting at 1.5 meter from B or C. This is a question given, and we need to find the unknowns here, all the forces. In general practice, in this method, we want to know the value of theta here. Usually, number of unknowns by kinematic indeterminacy means we can see here A is 0, B is having 1, C is having 1 unknown rotations here. So there are 2 unknown places where we need to assign the coordinate for these 2 joints. Instead of going that, we can make still more simple by not even applying the equations and find the equation of equilibrium and find the unknowns. Directly we can see that there are 3 joints A, B, C. Usually all joints will have a rotation, that is theta. But here in this A is a fixed joint. So rotation at A point will be 0, as you know already we have done in the slope deflection method. Since A is a fixed end, we doesn't get any rotation at A point, but we get rotation at B and C, which are roller support. So here we are assuming theta B and theta C are the redundant force, means the kinematic indeterminacy, which need to find here. So we can see here the step 2, we are assigning the coordinate at a point where we are taking the displacements. Here I am taking theta B and theta C as the kinematic indeterminacies. So we are assigning a coordinate of 1 unit rotation at B point and the second unit rotation at C point. So these are the 2 coordinates points which we have taken into account here. Then next comes the third step. Assume individuals beam as split into simply as fixed end moments. So member AB with a fixed end moment span of 4 meters with a 60 kilonewton entire span. So the fixed end moment at AB will be minus WL square by 12. W is 60 and L is 4 here. Substituting value of all these, we get minus 80 kilonewton meter as a moment for joint A for member AB. Similarly, the moment at B joint for member BA will be plus 80 kilonewton meter. Next, coming to second member BC, again B is fixed, C is fixed. Span is 3 meters. The distance of point load acting at its span of the member is 1.5 meter from C. So the formula to find the fixed end moments at B point and C point will be minus WL by 8. Substituting the values of W is equal to 100, L is equal to 3. The moment at B joint for member BC will be minus 37.5 and at C point it will be plus 37.5. Step is we are finding the PL value. that is final forces which is in step 6 here. We are finding it in step 4 itself. So PL value means we can see we have taken two coordinates, one at B and one at C. So total the moments acting at B joints are two members, BA plus BC. So MFBA plus MFBC. MFBA is plus here, plus 80. MFBC is minus 37.5. So next comes is the second coordinate point at C joint. So MFCB is equal to 37.5, that is plus, at C point it will be plus. So we can see PL is equal to MFBA plus MFBC equals to 80 plus minus 37.5 and plus 37.5. Total value we get for PL will be 42.5 and 37.5. 42.5 is the value at B joint and 37.5 is value at C point. These are nothing but the moments we are adding at individual joints. That is the PL value directly. After finding the fixed moments, we are finding the total moments acting at that individual joints. We are just adding them. So we get 42.5 is the added moment in B joint and 37.5 is the added moment at C joint. This will complete the fourth step. Step number 4, what we have found, that is determination of PL. Next is determine the stiffness matrix. Now the real picture comes here. So first coordinate is 1 here at B and second coordinate is C here. We are applying a unit moment at B point, that is 1 unit rotation at B point. It will be rotating, free to rotate. So we are finding the stiffness of member at joint B will be K11 and add that of at C will be K21. K11 means stiffness at first coordinate joint due to unit moment applied at first joint. K21 is stiffness at second coordinate joint due to unit load applied at first joint. That is K21. This is how we are finding. So K11 means what? Stiffness at B joint. B joint we have two members, KBA, KBC. So there are two stiffness adding here, KBA plus KBC. That will become a K11. K21 what happens? Only one member, that will be KCB. So KAB, BA means KBC, the stiffness at member BA plus stiffness at member PC. Stiffness of member BA will be what? You know slope deflection equation, that is 2 EA by L AB, that is BA, bracket of 2 times theta B plus theta A minus 3 delta by L. Minus 3 delta by L will be neglected because there is no settlement given in the members. So we will remove that. We will keep it only 2 EA by L, bracket of 2 theta B plus theta A. Since we are applied unit moment at a B joint, other than B, other than rotation at B, remaining rotations will be 0. When we are finding rotations in the other end, since we are applying a unit movement or unit rotation at one joint, that is B joint, remaining theta, whether it is theta A or theta C, they remains 0 here. So other than B, remaining rotations are 0 means theta A will be 0. Coming to theta stiffness of member BC, second member, 2 EA by LBC, 2 theta B plus theta C. As I told, it is a unit rotation applied at B joint, so only theta B will be there, remaining thetas will be 0. So making remaining theta as 0, that's theta A is 0 and theta C is 0. We are left with 2 EI into 2, that is 4 EI theta B divided by 4 plus 2 2s are 4, 4 theta B EI divided by 3. So we can see 4 EI by 4 plus 4 EI by 3, theta B is taken common. So when we take LCM, we get total 7 by 3 theta B. So this is a stiffness of joint B, that is K11, and a unit load is applied at K11. Next is K21. K21 is what? The member connected with the C joint is KCB. So KCB what is? 2 EA by LCB bracket of theta B plus 2 theta C. Because C is the first member, we get 2 times C, and B is the second member, we get theta B. But when we take K21, make sure that K21 is what? Stiffness at second coordinate joint due to unit load applied at first joint. That indicates you are applying unit load at first joint, also only theta B will be there, other than theta B will be 0. So theta C will become 0 here. So the formula left is 2 by 4 EI theta B, 2 by 3 EI theta B. So this is what the stiffness we got for member BA for coordinate 1 and 2 when the unit load is applied at B joint. Similarly, unit rotation is applied at C joint. That is, you can see the member here, ABC. We are applying a unit theta is equal to 1 in the C joint. For this, there is a rotation in the members will be in this fashion. We can see here, due to applied unit rotation at C joint, we get stiffness in member CB will be K22, at B it will be K12. So what is this K22? Stiffness at second coordinate joint due to unit moment applied at second joint. Similarly, K12 will be stiffness of member at a first coordinate joint due to unit rotation applied at second joint. This will be done, and we can see the due to applied unit rotation at C joint, there will be only one deflection in member CB. So K12 will be nothing but KBA plus KBC. KBA is 0, we cannot see any rotation here. So KBA is 0, and KBC, we are substituting the value, that is 2 EI by 3 bracket of 2 theta B plus theta C. We know that unit rotation is applied only at C joint. So theta B becomes 0 here, left with 2 by 3 EI theta C. And K22 is nothing but rotation at C joint. So for this formula is 2 EI by 3 bracket of 2 theta C plus theta B. Since the unit rotation applied at C joint, theta B becomes 0. So it will be 4 by 3 EI. This is how we get the rotation applied. Here also simply we can see unit rotation is applied at B joint, which makes rotation at both B and BC get both are rotated here. That's what we have taken 2 members. Here also same. B we get 2 members, BA plus BC, but due to unit load applied at C joint, we get rotation only at BC member, not along BA. So this is what we have got K value. Then find the final forces acting in coordinate directions. What they have given 1 and 2. We know that P is equal to 0, 0. There is no any additional moment at B and C joint before going for this equation. No external moment is given at B or C. So the both are taken as 0, 0. Next comes is step number 7, that is stiffness equation. We are substituting the stiffness equation is, that is K into delta equals to P minus PL. K, we know that it is K11, K12, what we have applied. That is 7 by 3, 2 by 3, 2 by 3, 4 by 3. That is divided by EI. K11, K21, K21, K12, K22. Substitute value taking 1 by EI as common into delta. The unknowns here we have taken are theta B and theta C, because we have taken rotation at B as well as we have taken rotation at C here. So theta B and theta C. This is equal to, we can see here, capital P here, 0, 0. No external rotation given in the question paper. That's what theta P value will be 0, 0 on both the sides. Minus of PL, what we have found in the fourth step. That is, we can see here, fourth step we have found PL. PL is equal to the summation of moment at individual coordinate joints. So at first joint, the moment combined will be 42.5, and the second joint, the moment will be 37.5. Same will be substituted here. You can see 42.5, 37.5, but it is minus here. So bracket closed. When we substitute the values and we read the equations, the first equations becomes is row into column, 2.33 into theta B, 0.667 into theta C is equal to minus 42.5. 0.66 into theta b, 1.33 into theta c is equal to minus 37.5. So these are the two equations what we have got here to solve the problem, and even we can see the unknowns are two here, that is theta b and theta c. Now using the equation of equilibriums, we can find the unknowns here. So by equation of equilibrium, we came to know that by calculating through calculator also we get results at a theta b will be minus L1.875 by EI, and similarly the rotation at C joint will be minus 22.18 divided by EI. Since theta A is 0, as it is a fixed and it is not being taken into consideration. Only theta B and theta C have been substituted here. That is minus 7.87 and minus 2.18. So once you know the rotations at both the joints B and C, well, rotations of other end is 0, we can find the final moments by substituting this in slope deflection equation. So here we can see the final moments are found by applying a slope deflection equation. You can see what is our slope deflection equation here. MAB equals to what? MFAB plus 2EA by LAB, bracket of 2 theta A plus theta B minus 3 delta by L here. Since the supports are being firmly here, rigid here, there is no chances of settling in the supports. That's why delta becomes 0 directly here, and we have left with other two variations, theta A and theta B. Theta A is 0 as it is a fixed, and we get theta B. Substitute all values, we can see here MFA is minus 80, 2 EI divided by LAB. EI is same here. LAB is nothing but a 4 meters. So theta B is minus L1.875 divided by EI. Knowing this, substitute the values, we get the moment will be 80 minus 80. This 2 by 4, that is 0.5 EI into minus 11.875. This will become 5.94. So adding this also minus, adding both, the final moments at A joint for member AB will be minus 85.94 kilonewton meter. So this is how we got the moments by applying the equation of the slope deflection equation. Similarly, find the final moments in the other members also, at other joints also. So coming joint B here, we are taking member BA. You can see the formula will be MFBA bracket of 2 EI by L BA bracket of 2 times theta B plus theta A minus 3 delta by L. Delta is 0, theta A is 0, left with only delta B. Theta B is nothing but minus L1.875. Substituting this value, we get fixed end moment at B joint for member BA will be 80 plus 2 EI by 4 bracket of 2 times theta B, that is minus 11.875. So putting this value, we get 4 by 4 cancels, left with minus 11.875 plus of 80, we get 68.125 as the moment at B joint for member BA. Next member is BC. Substitute same formula here also. A fixed end moment at B joint for member BC will be minus 37.5 plus 2 EI by L, that is 3 here, span between BC, bracket close, 2 times theta B will be minus 11.875. That of theta C is minus 22.78. Adding all this, the final moments at B joint for member BC will be minus 68.11. So this is how we found all the moments here. Once you got the moment, the final moment at CB will be 0 here. Since at the end, we can check it. If you check also, we get 37.5 plus 2 EI minus 22.78 plus 2 times 22.78 plus 11.875. Adding all this, we get at a moment, free end moment at C, D to C point will be, C to B point will be 0. This is how we got. So method is very simple, guys. You need to find the steps easily. Steps are shown here. How to find the steps are clearly written. Just follow the steps, analyze the things. It will become quite easy. Don't neglect the things. A simple way I have told to remember how to solve this. Instead of finding kinematic indeterminacy, going with the formula and detecting with the unknowns, it will be difficult. Simply, I have told you a simple method to find the unknowns. That is kinematic indeterminacy. What is degree of kinematic indeterminacy for this member? As I told you, number of check the number of joints. The number of joints in this are A, B, C, and we know that A is a fixed end. Obviously, theta A will be 0. Left with two thetas, that is theta B and theta C. Theta B, you know already, it is having a rotation at B joint, and similarly, BC is also having a roller support, so it will also has a rotation in this. Once you know there are two unknown rotations, theta B and theta C, we need to get two equations to solve this. So to solve this, first step, as I told, we are assigning the coordinates at the joints which are being removed here. So coordinates are theta B and theta C, which are not there in the present conditions. So step 3, splitting individual members as a fixed end moments subjected to the loads what you have got earlier, external loads. For that, we find the fixed end moments at individual joints. So member AB is considered. We get moment at A and moment at B. Similarly, consider member BC, find moment at B and moment at C. In this fashion, we are going to calculate the moment at every end. Next is step 4. Step 4 is simple. PL value, as I told, adding the moment at a coordinate joints. Which are coordinate here? The removed two thetas, theta B and theta C, because theta A is 0. So two coordinates are there. We are finding the fixed moment at B, adding fixed moment at C. Here there are two members are connected. So here the one member is connected. Whether it's plus or minus, add them. Final moments what we get will be the PL value. Then we apply unit movement at individual direction in the same direction which are been removed here. So theta B, we have taken it clockwise. Similarly, we have taken theta C as a clockwise. Then we are finding the stiffness at individual members, and we are finding the final moments. Once we get the stiffness, and here one thing I want you to keep in mind, when we find K11 or K21, when you write this equation, whole equation, you can see here, we have written the equation 2A by LAB, theta B plus theta B, where rotation is applied, at which joint we are applying the unit rotation, that rotation will be active. We are applying rotation at B joint, only theta B will be active. Other than this rotations, that is whether theta A or theta C, they remain 0. That's why theta A is taken 0, theta C is taken as 0. Adding all this, we get stiffness of individual members. Once we get stiffness of individual member, find the final forces, form stiffness equations, that is K delta into P minus PL. Substitute individual forces, what we have got here. You can see here, once we got this whole equation, using a calculator, find the unknowns rotation at B and C we have got. Once we got the rotation at B and C, we can get the final moments by taking into consideration the slope deflection equations. Substitute these values in slope deflection, we get the final moments. Once you forget the final moments, you need to draw the B and D. So this is all regarding the first method. The last model, the first class what we have started, stiffness. Go through the notes. First know the steps here, what to be followed. Then analyze it will become easy for you. Okay? Is anybody having any doubts here? Friends, anybody is having any doubts? If yes, we will clarify the things. So no doubts. No problem. If you don't have any problems, if you don't have any doubts, We can close the session here. So anybody is having any doubts here? No doubts?
Sir,
Yeah. Hello? Hello? Fine. No doubts? Let us conclude it. Hmm? Okay, guys. Thank you for patiently listening to the class and completing this. Okay? Thank you.